like if you have two reactions, one supposed to be oxidation and one supposed to be reduction, and you add them up and you get the reaction at the end, that is cell reaction. You need to be able to convert K's to delta G's, or potential, standard potential to delta G, stuff like that. I don't have any example here, but whatever I did in class, you're responsible. Whatever you have in homework, please check it. Okay. What else? Yeah, for ion selective electrodes, you just need to know this one for this exam. For the final, all of them. I would say that's kind of it for electrochemistry, right? Did I miss something? I think that's kind of it. So we are moving back to fluorescence and stuff like that. Okay, for absorption and emission, you need to know the names for all processes. I forgot to put numbers, guys. Let's put some numbers and call these processes. And I just had 5, but you're responsible for all of them. So let's just discuss it. If we go from the ground state to the excited state, what is it? Absorbance. How long does it take? 10 to the negative 15 seconds usually. What is this? Number 2. Vibrational relaxation. Whenever the molecules started to increase amplitude of their specific vibrations. Okay? Up here, guys, if we go back to the ground state, the photon is emitted. And this is taken much longer, okay, up to 10 to the negative 5 seconds, and it's fluorescence. So fluorescence is the emission of electrons. We could go up to here. If we have many vibrational rotational states, we could go, and what happens? What is that? How do we call this process?
Internal conversion.
Internal conversion. We do not change singlet to something else. It was singlet excited, it's singlet ground. Okay, internal conversion. That process is very fast, okay? And whenever we go down, what is this? Vibrational relaxation again. A lot of vibrations happens and maybe rotations, and the molecule has a good time dancing. And no photons are emitted. Just the environment is heated. All right, if we are still here and we go from singlet excited to triplet excited, what is that? Inter-system crossing. We go from one system to another. This is actually prohibited process. It means probability for it is much lower. It takes much longer for this to happen, up to 100 seconds, because this inter-system crossing is not very probable process. Okay, R3 is what? Vibrational relaxation again. Some energy was lost to vibrations. So amplitudes of some vibrations increased. Energy was lost because the environment was heated. No photons were emitted here. We could go from here to here. What is that? Another inter-system crossing. We go from triplet excited to ground singlet. Systems are different, that's why it's inter-system crossing. And we could have another vibrational relaxation, and all of that will not emit any photons. Okay? If we were still here and we go down like this, it's a phosphorescence, a photon is emitted here. Good? All right, very nice. So I guess you can name them now. You need to know all of them. Okay, I don't know if I give you that or not, but you have to know. Be proud. Okay? All right, what is the difference between fluorescence and phosphorescence? Which one is emitted at low wavelength? Please explain. So we are comparing fluorescence to phosphorescence. Okay? Fluorescence to phosphorescence. What's the difference? First of all, if we go from S1 to S0, right? Singlet excited to singlet ground. And the photon is emitted. That's fluorescence. If we go from a triplet excited to a singlet ground, that's a phosphorescence, right? Also, we can say that fluorescence is much faster. It's up to 10 to the negative 5 seconds, while phosphorescence is a much longer process. It can take up to 100 seconds. So it's not very common. It's very, it's very low probability process to do intersystem crossing. That's why the rest, and we are going from triplet to singlet. It's very low probability process, okay? So it does happen, but it's rare. And let's see what else we can talk about. Which one is emitted at longer wavelength? So these two are emission processes. That's it. We don't have any other emission processes where photons are actually emitted. All other stuff is whenever energy is lost and the environment is heated, but photons are not emitted. But which one will have longer wavelength? Fluorescence or phosphorescence? Okay, that's good. Why? So usually it looks like this. This is absorption, this is fluorescence, this is phosphorescence, right? If you put the wavelength up here and intensity of different processes up here. So first of all, absorbance is very common. There is a huge probability for absorbance. That's why it's so high in intensity. Fluorescence is not as common, and not every photon that was absorbed will be emitted. So its intensity is much lower than absorbance. And also it's red-shifted. Why? Because some energy is usually lost due to vibrational relaxation. The energy is lost means we go to longer wavelength. Because energy is h nu or hc divided by wavelength. The wavelength goes up, it means energy is going down. Or energy is going down, it means the wavelength goes up. Okay, so fluorescence is red-shifted usually comparing to absorbance. What about phosphorescence? Look, we lost some extra energy due to vibrational relaxation here. And that's why phosphorescence is even less energetic than fluorescence. That's why we go to even longer wavelength. Smaller energy means longer wavelength. And if you think short wavelength is where we have blue light, and longer wavelength is where we have red light. So if you shift to longer and longer, it means red shift. If you move to shorter and shorter wavelength, it means blue shift. Okay, good? All right. Questions? All right. So you have have an electrochemical cell